Hello, MAT134 students. This is test 2 review. Uh, I have prepared 5 to 6 questions to do, which covers everything. But before starting, let me mention that these questions are a little bit longer or more computationally more involved than the questions that you would expect in the test. So if you see they are long, I just wanted to cover many different things in our test review, and not all these steps you will be needed in test two. So you will be tested on some selected methods. First question, it's about volume of a solid of rotation, and also involve some trig integrals to compute. So we have this shaded region, this green region that is rotated about x-axis, and I want to compute the volume of the resulting solid. So first, to set up the integral for the volume, I have that. I can see that because I should rotate about x-axis. I need to do cross sections perpendicular to x-axis, and these cross sections for this green region starts from here, ends here. But from here up to here, the cross section is trapped between the red curve and the blue curve, and after that, it's just between the red curve and the x-axis. So I need to divide the integral into two pieces. First piece is from here to here, which is from pi over 4 to pi over 2. And a typical cross section has this. When I rotate it, I get a washer. The outer radius of this washer, it's the height of the red curve. So I have pi, the outer radius squared. The outer radius is the height of the red function. So it will be sine x squared, or let me just write it sine squared x. The inner radius, which in this picture is like this, it's the height of the blue function. So this is the inner radius, and then I have minus inner radius squared. So this is the first integral. The second integral that I need, it's from here up to here, which is from pi over 2 to pi. And now if I do one cross section and I rotate about x-axis, I see that I get a disk rather than washer. So I have just pi radius of this disk, which is the height of the red function, so sine squared. This is the setup of the integral. The rest of this question, which is computation of this, it's about trig integrals. Recall that for an integral involving an exponent of sine and cosine, if I have odd number of sine or cosine, it's good. And when I have good number of something, I do u substitution, u equals the other one. For example, if this is odd, I use u equals cosine. Or if this is odd, I use u equals sine. But in these integrals, if you see, all of them are even. That means that I cannot do substitution directly. What was the strategy when both of them were even? It was that I need to use the formulas sine squared and cos squared are 1 plus minus cos 2x divided 2. So if I use those formulas in the first integral, I can take this pi outside as a coefficient. This pi I'm talking about. And then sine squared is 1 minus cos 2x divided 2 minus cos squared is 1 plus cos 2x divided 2. And in the second integral, again, let me take this pi out as a coefficient. I have sine squared is 1 minus cos 2x divided 2. So if we simplify this, we get that this, note that it's 1 over 2 minus 1 over 2. They cancel each other. And then it's minus cos 2x divide 2, another minus cos 2x divide 2. So in total, it will be minus cos 2x. So this parenthesis is minus cos 2x. Now it's matter of finding antiderivative. Antiderivative of minus cos, it's minus sine. Derivative of sine is cosine. But because the inside is 2x, if I also apply the chain rule, I need a divide 2 to make sure that after taking derivative from this, I get exactly that without the coefficient. So this is antiderivative of that. Then I plug in pi over, by the way, this bottom one, it's pi over 4. I plug in pi over 4 and pi over 2 in this. For the second integral, antiderivative of 1 over 2 is just x over 2. If you like, first let me take this 2 outside beside pi, so to have pi over 2. And then antiderivative of this. Antiderivative of 1 is just x. Antiderivative of cos 2x, it's just what we computed here. It's sine 2x divide 2. Now I need to evaluate at pi over 2 and pi. Now I'm good to start the numerical computation. So the first term, if I plug in pi over 2 in it, I get minus sine twice of pi over 2, which is pi over 2, plus, which is minus, I get plus, sine, now plug in pi over 4 in this. So twice of pi over 4, it's pi over 2, over 2, plus pi over 2, plugging pi in this, you get pi minus sine 2 pi over 2. And then when you plug in pi over 2 in this, you get pi over 2 minus sine twice of pi over 2, which is pi, divide 2. Sine pi, it's 0. Sine pi over 2, it's 1. Sine 2 pi, it's 0. And sine pi uh, is also 0. So what do I get in total? It's pi 0 plus 1 over 2 plus pi over 2, pi minus 0 minus pi over 2 minus 0. So pi minus pi over 2. So this is pi over 2, pi minus pi over 2, and this is just 1 over 2. So the first term becomes pi over 2, this in total. And the second term is pi over 2 times pi over 2, which is pi squared over 4. So this is the volume that we needed to compute. Okay, now let's move on to the second question, which it should be obvious by the way, it's very good to pause the video before each question and try it yourself before looking at my solution. So by looking at it, it should be very clear that I should use integration by parts. Whenever I have logarithm or arcsine, even as a single term inside integral, you should use integration by parts. And the best choices for you in integration by parts are logarithm and inverse trig function. So I do a integration by part by a choice of u equals arc sine x squared, whatever I have here. There is only one term in the integral, and that should be u. The rest of it, which is just dx, should be dv. Hence, v should be x, and the du should be derivative of this. Using chain rule, it's 2 arc sine, then times derivative of arc sine. Derivative of arc sine is 1 over root 1 minus x squared. Don't forget to add the x as well because it's differential. Now applying the integration by parts. I have uv this times this, which is x arc sine squared x minus v du. So that is x 2 arc sine x over root 1 minus x squared dx. If I rewrite this expression, the first term, I don't need to do anything about it. It's just computed. But this indefinite integral, now I need to compute indefinite integral. By looking at it, again, I have logarithm or inverse trig functions, and I have product of two different type of functions. Both of these strongly suggest that I should use integration by parts again. And the best choice for integration by parts, for u in integration by parts, it's inverse trig function and logarithm. So this should be my u. Everything else should be dv. So let me isolate that as u and write everything else as like one group. So this should be dv, this should be u. To do this computation of this second integration by parts, let me just do it as a separate example, and then when I have the answer, I will bring it here. I don't want to write this extra term over and over when I'm computing this, and that would be waste of time. So let's compute this green integral separately, and then when I have the answer, I will plug in here. So now let me focus on computation of this. As I mentioned, it should be an integration by parts, and this is u, this is dv. So if I do that, u equals arc sine, and the dv equals this, which is 2x root 1 minus x squared dx. Then du is derivative of arc sine is 1 over root 1 minus x squared times dx. And now I need to compute v. But computation of v, basically antiderivative of this, itself is a separate integral that needs a substitution. Why it needs substitution? Because I see something in a layer and I see derivative of it on top. So it's a substitution. Let me do this as a side example. Antiderivative of 2x over 1 minus x squared. What is it? If I do a substitution, t equals, as I mentioned, 1 minus x squared. Why I don't call it u? Because I already have u here and I don't want to use the same letter more than once in one computation. So I use another letter, t, or if you like, w. Then dt, it's derivative of 1 minus x squared is minus 2x dx. So if I do this substitution, this is t, so it's root t in the denominator. And this all together, 2x dx, it's this, which is minus dt. Okay, good. Now, how should I compute this integral? This is very simple. It's just one single power term. It is minus, I can take this minus out, and then write t, root t as t 1 over 2, but it's in the denominator, so negative 1 over 2 on top, dt. Antiderivative is increase the exponent by 1. I have this extra negative sign on the back, and then increase the exponent by 1, divide by the new exponent plus c. And this is in terms of t. I need to replace it in terms of my original variable. T is 1 minus x squared, replacing it to the exponent 1 over 2 means root t, but t is 1 minus x squared. Over 1 over 2. Over 1 over 2, I can bring this 2 on top, and I get twice of that. And I have this extra negative sign plus constant. So this is the value of this integral. In other words, I showed that if dv is this, then v itself, it should be this. But one of them is enough. This is all antiderivatives of this function. So v is just one of them. I take the simplest one when c is 0, or when I don't have any c, and I can take v is less. Recall that in integration by parts, we don't get involve any constant until the very last step, that there is no more indefinite integral. Okay, so I found du and v. Now applying integration by parts to this integral. So I have uv. This is minus 2 root 1 minus x squared arc sine x. Then minus integral v du. So it's minus 2 root 1 minus x squared. That's v du. Root 1 minus x squared. 1 over root 1 minus x squared dx. This and this cancel. And this minus sign and minus sign also cancel. So you get positive, minus minus, it's positive. Integral just 2. Antiderivative of 2 is 2x. Plus a constant. Now that I have the answer for antiderivative of this expression, I will replace it here. This is antiderivative of this that I found with a second integration by parts. The reason that I did this separate computation is that if I could do it here, but every time that I would write this, like this, every time that I would write a line of computation, I needed to copy this, copy this, copy this, copy this, and that was a waste of time. So I did that computation separately. Now that I have the answer, I plug in here. So the final answer is this minus the answer of this one that I computed separately. And don't forget to add a general constant. That constant should be added whenever there is no indefinite integral anymore. Okay, so basically the final answer is, if you apply this negative sign to this parenthesis, you get positive, and then here negative. So this is the final answer for antiderivative of arc sine squared. Okay, good. Next question. is a trig substitution, but during doing that, I need trig integrals as well. But first, let's start the trig substitution. So it is very clear that it's trig substitution because I have a number plus x squared. Whenever I have a squared plus x squared, I would do x equals a tangent, this substitution. Whenever it's a squared minus x squared, I do a sine theta. And whenever it's x squared minus a squared, I do a secant theta. These are the choices of trig substitution. In this case, it's tangent one. So I have x equals, what is a? This is a squared, which is 9. So a is free. So it's free tangent theta. This is the substitution that I should do. So taking differential, dx is free derivative of tangent is secant squared theta d theta. And then let me substitute everything in this. So I have 9 plus x squared. Let me, using this, compute it separately to just replace the whole thing. So 9 plus x squared is, x is free tan theta. So it's 9 plus 9 tangent squared theta. X is free tan theta. So x squared is 9 tangent squared. Factoring 9 out of it. And noting that 1 plus tangent squared is secant squared, I will get this. So let's do the substitution here. So this part, it's what I computed right now, 9 secant squared theta. The whole thing to the exponent 3/2. I replace this part with 9 secant squared according to this computation. On top, I have this cubed, but free, or let me just write free tan theta cubed. Also, I need to replace dx. dx is this. It's free secant squared theta d theta. Now I need to simplify. So raising this to the exponent 3, you get 27 tangent cube theta. Applying this 3/2, you can consider to the exponent 3/2 as over 2, it's root. So I have root of 9 secant squared to the exponent 3. 3/2, it's the same as exponent 3. And also exponent 1/2. Exponent 1/2 is root. Okay, good. Now this is free secant. If I compute this, this is free. Root 9 secant squared is free secant. And then raising it to the exponent 3, you get 27 secant cube. On top, I had 27 tangent cubed and 3 secant squared. Simplifying 27 and 27 and partially sum of the secants with each other, I would get only 3 on top. So the number 27 and 27 cancel. I will get only number 3. So 3. Then how many I have tangent cubed. And simplifying this and this, I have 3 secant in the denominator, 2 secants on top. So in total, 1 secant in the denominator. D theta. That's what I should compute. Let me take this constant 3 outside and compute this. This is an exponent of tangent times exponent of secant. If you remember, when I have this and I want to compute, odd number of tangent is good and even number of secant is good. So, and whenever I have a good thing, I do u equals the other one. Substitution u equals the other. So, if this is odd, then I do u equals secant. If this is even, I use u equals tangent. In this case, this is odd. The exponent of tangent, odd number of tangent is good. So I can use a substitution on this. U equals the other one. So I use a substitution. U equals secant theta. Note that I need odd number of tangent. I have odd number of tangent. That's good. I use U equals substitution. U equals the other one, which is secant. So up to here, it was trig substitution. Now it's a trig integral that I'm computing. It's like two examples in one. As I mentioned, these are longer in test. You won't have like many different techniques combined in each other in one question. They are shorter. But I just wanted to cover everything in my review, so that's why I decided to do longer questions. Okay, so if I want to do this substitution, u equals secant, derivative of secant is secant tangent. Then I isolate du, this thing. I isolate it, secant theta, tangent theta, d theta. I will write the rest here. So I had originally three tangent on top. One of them, it appeared here, I used here. So two more remain that I will have here. Good. I had originally only one secant in the denominator, but now I have added one other secant on top. I didn't have any secant on top. So to make sure that this expression is the same as this, I need secant squared, one extra secant other than this in the denominator to make sure that this cancel one of these, and then I get one the same as I had here. I had only one in the denominator. I added one extra one on top, but I need also to divide by that. I don't want to change my question. So this is what I get. Now I do the substitution. U is secant, so this is u squared. This is du. And finally, this one. Using the same identity that I used here, 1 plus tangent squared is secant squared. I can say that tangent squared is secant squared minus 1. 1 plus tangent squared is secant squared. So tangent squared is secant squared minus 1. But secant is u. So this implies that this is u squared minus 1. Tangent squared is secant squared minus 1. Secant is u. So it's u squared minus 1. Okay, so after this substitution, I got this integral to compute. But this is very simple integral to compute, because if I consider this and this, then I have only power term. The first term is just u squared over u squared. It's 1. The second term is 1 over u squared. Now I need to find antiderivative of these two terms. Antiderivative of the first term is just u. Antiderivative of second term, it's positive 1 over u. Derivative of 1 over u, it's negative 1 over u squared. If you like, you can consider this as a power term u minus 2 and use power rule. Increase the exponent by 1, divide by the new exponent to find the antiderivative. I have one extra minus sign on the back, and this is exactly 1 over u that I got. It's just simple power rule plus constant. So this is basically uh, almost end of the computation, but the problem is that I found the answer in terms of u. My question was in terms of x. It should be necessarily in terms of x. So I need to replace, I did two substitution. This is one of them, this is another one. I need to replace them back. So first I need to replace this u in terms of theta. I have that u is secant theta. So this means that I have secant theta plus 1 over secant theta plus c. Let me continue this computation on the next page. Okay, good. This is the same as secant theta. 1 over secant, or secant is 1 over cosine, or 1 over secant is cosine. Okay, good. But now my answer is in terms of theta. I need to have it in terms of x. So I should use this also substitution to write everything in terms of x. So I should use the fact that the relationship between theta and x is this. In other words, moving free to the other side of equality, tangent is x over 3. How would I write secant and cosine in terms of x? I need to use a reference triangle. If I have a right angle triangle with one of the angle theta, then tangent theta, it's opposite over adjacent, but it's x over 3. So let's say opposite is x, then adjacent is 3. Tangent theta, it's opposite over adjacent, which is x over 3. What would be the hypotenuse? I use Pythagorean. I get this squared, which is 9, plus this squared, which is x squared. Root 9 plus x squared is hypotenuse. Now from this triangle, I can read what is secant and cosine. First, what is cosine? Cosine is adjacent over hypotenuse. So it's 3 over root 9 plus x squared. This is cosine. Cosine theta, it's adjacent over hypotenuse. So it's 3 over root 9 plus x squared. What is secant? Secant is 1 over cosine. So it's like basically swapping top and bottom of this. So it's root 9 plus x squared divide 3. This is secant. So this is my final answer in terms of x. I can simplify it a little bit by expanding 3. This 3 and 3 cancel. You get root 9 plus x squared plus 3 times 3. Now it becomes 9 over root 9 plus x squared. And then by combining these into one fraction or taking the common denominator, so this one has no denominator, it's 1. So I need to multiply and divide by root 9 plus x squared. But root time, or in other words, root squared, it cancel root, and you get just 9x squared plus 9. So this is this fraction, and this is this. By multiplying and dividing by denominator, root 9 plus x squared. Plus c, and 9 plus 9, it's 18, plus x squared over root 9 plus x squared plus c. So the simplest, the most simplified version of the answer is this. Look uh, how nice this question is. We did tricks, obviously, very non-trivial computations trig substitution, trig integrals with involving tangent and secant, replacing everything back in terms of x, and we got this simple antiderivative. So basically, you can check it as an exercise like in MAT132 and take derivative from this. Use quotient rule and chain rule to see that you get this as the result. So it's not at all clear by looking at it that it has such a simple antiderivative, but by systematic computation of trig substitution and trig integrals, we can find the antiderivative. It's very nice. Okay. Next question. Obviously, we have polynomial over polynomial or rational function. So you should use the technique of integration that you should use is partial fraction decomposition. Okay. Let me first, for partial fractions, first, if degree of top is greater than the bottom, I need to do line division. But it's not the case in this question. This is degree 3, degree 4, so it's less than the bottom. Degree of top is less than the bottom. I don't need line division. Next thing is to factor the denominator as much as possible to get linear terms or irreducible quadratic terms. So factoring this. First, I use difference of squares. This is x squared minus 1 squared. So it is x squared minus 1, x squared plus 1. Then this is also difference of a squared. I factor it again, x minus 1, x plus 1. But this is irreducible. So I will keep it as it is. This is the denominator. Now I want to write down the partial fractions of this. In the denominator, now I have this after factorization. So contribution of this term, it's a linear term and its multiplicity is 1. So it has only one contribution with the same denominator, but because one lower degree than linear is constant, I have one constant on top. Contribution of the next term, it's again linear, degree repetition 1, multiplicity 1. So it has contribution 1 contribution, and on top I have one lower degree than the bottom, which is constant. Contribution of this term, it's irreducible quadratic and its multiplicity 1. So it has again one contribution, but because one lower degree than quadratic, it's linear. On top, I have a linear term. Note that degree of denominator is 4, and I have 1, 2, 3, 4 constants to find, 4 unknowns to find. To find the unknowns, I need to combine these into one fraction, like here. So if I do that, the common denominator is just x minus 1 times x plus 1 times x squared plus 1, multiplying these by each other. Then for the first term, what's missing in the denominator compared to this? It's these two terms. So I need to multiply and divide by these two terms. I get a x plus 1, x squared plus 1. The second term, its denominator is this, which is this term. So these two terms are missing. I need to multiply and divide by this. Multiply by missing terms. And for the last term, cx plus d, its denominator, it's only this term. So these two terms are missing. I multiply and divide by it. And I get this. These two terms together, if you like, it's x squared minus 1. Okay, so I get that. this, let me write this also as well. X squared minus 1. This fraction is the same as this fraction, but they have the same denominator. So the top of this also should be the same as top of this. So it's equals to x equals to this. Good. Note that I have 4 unknowns. If I want to do it directly, I need to write down 4 equations in 4 unknowns and solve 4 unknowns. But that's a lot of computation. So make sure that take advantage of the simple thing that I mentioned in the class and use for each linear term, find one of the unknowns. For each of these linear terms, I can find one of the unknowns. How? By replacing the root of that linear term in this equation. So this linear term has root 1, x equals 1. So at x equals 1, don't forget. At x equals 1, you get, putting 1 in this, you get 1 minus 4 minus 3 minus 2, that's the left-hand side, equals. Then you put 1, this becomes a times 2 times 2. But the second term becomes 0 because 1 minus 1 is 0. This term also becomes 0 because 1 minus 1 is 0. So you get this is negative 3, negative 6, negative 8. So you get negative 8 equals 4a. Hence, a is negative 2. I found one of the unknowns. For the other linear term, I do the same thing and I find another unknown. At x equals negative 1, this one is negative 1 cubed, negative 1, minus 4, negative 1 squared, it's just negative 4, minus 3 times negative 1, it's positive 3, and then negative 2. Putting negative 1 in this, that becomes 0 because of this term. Putting negative 1 in the middle term, you get b minus 2 minus 1 minus 1. And then minus 1 squared, which is 1 plus 1, so 2. Plus, now this term also is 0 because of this. Note that that is this times this. So when you put negative 1 in it, you get 0. This is negative 5, or this is 1, cancel this negative 1, so you just get negative 4 equals negative 4b. 4b is 1. Good. Now I can't find more unknowns using this strategy because I had only two linear terms. I found 2 unknowns. But now if I replace these 2 unknowns that I found in this equation, I won't have 4 equations in 4 unknowns. I would have only 2 unknowns, and that's much easier to solve, much less computation. So if I replace that, so I get that this with a equals negative 2, b equals 1 is, let me simplify it. Expand and simplify. First, expanding these, I have negative 2, this times this, which is x cubed. Then negative 2, this times this, which is x. Then negative 2, this times this, which is x squared. And finally, negative 2, this times this, which is 1. or times negative 2 times 1, which is negative 2. Plus, now expanding this. X times x squared, it's x cubed. X times 1, it's x. Minus 1 times x squared, it's minus x squared. Minus 1 times 1, it's just minus 1. Plus, now expanding the other one, this times this, which is cx cubed. No, this times this, it's minus cx. This times this is dx squared. And finally, this times this is minus d. If I group terms together, I have something x cubed plus something x squared plus something x plus a constant. What are x cubed terms? X cubed terms are this, uh, and I think that's it. By the way, yeah, negative 2 plus, yeah, and I see my mistake. This times this is also x cubed. I wrote it as x squared. That's a typo. I was expecting 3 terms x cubed, but I had 2. I noticed that I had a computational mistake. This is x cubed. I had negative 2x times x squared, which is negative 2x cubed, not s squared. Okay, good. I have 3 x cubed terms, this. What are the coefficients of them? C, 1, and negative 2. So here I have C plus 1 minus 2, which is C minus 1. Then x squared terms. I have this term, and this term. So it's D, the coefficients, D minus 1 and minus 2. So it's D minus 2 minus 1. In total, it's D minus 3. X terms, it's this one, and this one. So it's minus C, 1, and negative 2. Minus C, 1, and negative 2. 1 minus 2, it's negative 1. So it's minus C minus 1. And the constant terms, it's this one, and this one. So it's minus D minus 1 minus 2. So it's minus D minus 1 minus 2. It's minus 3. This is this after replacing A and B that we found. But it is equals to this. It is equal to this. This means that x cubed terms should be the same, but here I had only one x cubed. 1x cubed should be that. I have negative 4x cubed. X squared. Negative 4x squared. And then I have negative 3x. And then I have minus 2. So this means that this is this, this is this, this is this, and this is this. One comment. Now I had all of them. But for example, if this was missing here, then x squared terms missing means I have 0 x squared. So I would say I have 0 x squared, and this would be this, for example. Okay. Now I have a simple equations to solve. This is this, or C minus 1 is 1. This implies that C is 2. And this equation is d minus 3 equals minus 4. So this means that d is 3 minus 4 or negative 1. I have two more equations. If I haven't solved this A and B, I needed them to find all four unknowns. But now they are extra. You can either skip them or a very good recommendation is when you found them, use the extra equations to make sure that you haven't done computational mistake. So make sure that these equations are also satisfied. Are they satisfied? Let's check. C is 2. If you put C equals 2 in this, you get negative 2 minus 1, which is negative 3. So good, I haven't done any computational mistake. And in this equation, if I put D equals negative 1, D is negative 1. You get negative negative 1, which is positive 1 minus 3. It's negative 2. Good, this also matched. So I haven't done any computational mistake. And these are A, B, C, and D. Now that I have A, B, C, D, let me replace them in this partial fraction decomposition and start integrating. So the original denominator was x squared, x to the exponent 4 minus 1. Let me keep it like that. So I found this partial decomposition with A equals negative 2. B equals 1. C equals 2. And D equals negative 1. So this is the conclusion of partial decomposition step after finding the unknowns. What was my goal? To compute antiderivative of this. The whole point of this partial fraction decomposition is instead of computing this more complicated antiderivative of rational function, I have I can break it into simpler and easier integrals like this. Okay, integral dx or let me first, I don't have enough space here. Let me just keep it as the partial decomposition first and then break it into simpler integrals. I just need a little bit more space for dx. Okay, good. So I had that partial fraction decomposition of that rational function is this, and now I integrate. So let's do integrate term by term. Integral of this is 1 over x minus 1. Its antiderivative is ln absolute value x minus 1 with the coefficient minus 2. Antiderivative of this, it's ln absolute value x plus 1, and the coefficient is 1. To compute this last integral, which is this, I need to divide it into two integrals, this and this. Why? Because if I had this and I would have constant on top, then I knew that derivative of arctangent is 1 over x squared plus 1. So I knew that antiderivative of constant over x squared plus 1, it's an arctangent. On the other hand, if I have this without that constant term, I see something and derivative of it is on top, which I can use a u substitution in it. So if I separate this into two integrals, each of them, it's easy to compute. So consider one integral, which is this, the other integral, which is this minus 1 over x squared plus 1. Good. I have these first two terms untouched. This last term, as I mentioned, derivative of arctangent is 1 over x squared plus 1. So it's minus arctangent. Don't forget to add constant. What about this term? You need a substitution. You need to do in the this integral, you need to do a substitution. U equals x squared plus 1. I will skip the intermediate steps, but that's U. This is du. Let me do this substitution in another color to make it more clear. So doing substitution, u equals x squared plus 1. This is u. Derivative of x squared plus 1 is 2x. And du will be 2x dx. This is du. Basically, I would get integral du over u, or 1 over u du. Antiderivative of 1 over u. It's ln absolute value u, but u is x squared plus 1. So replacing x squared plus 1, I would get this. But x squared plus 1, it's positive, so I don't need absolute value. And I get ln x squared plus 1. And this is the final answer for our questions, for this question. As you see, partial fraction decomposition method, it's very powerful. If you have any basically rational function, it systematically decompose it into simpler components, and each of the components it's easy integral to handle. Good. Now we have reviewed all techniques of integration after test 1, which was integration by parts, trig substitution, trig integrals, both tangent secant and sine cosine, and partial fraction decomposition. With also one example of like volume of a solid of rotation. That should be in, it's not, of course, every single topic. For example, improper integrals. Definitely you will have questions about improper integrals in test 2, but I can't do one question of everything in one review session. So this is not everything, but it's the main techniques of integration that we have seen. I did at least one question from each. Now let's do a couple of questions on series as well. I won't do any sequence question, but you have that as a content of test 2, and probably you have questions from sequences as well in test 2, but sequences are simpler than series. That's why I decided to do series. Basically, in computation of series, we also involving some sequence usually. So that's more complicated, but make sure that you also review sequences. Okay, so we have two questions. We want to compute the exact value of these two series, if they converge, and if they diverge, show that they diverge. Note that, let me recap whatever we have seen before, until the end of test 2, before this week, about series. First of all, we have seen that we have 3 basic series. 1 of them is telescoping. then geometric, and also P series. These three are like basic series that we can directly answer if they are convergent or divergent. We have an easy situation in these three cases. The other complicated series, we use different tests on them to see if they are convergent or divergent. The tests that we have seen until now, we have more after test two, but until end of test two, they are four tests. One of them is divergence test, then integral test, direct comparison test, and limit comparison test. These four. Note that when you use tests, you only get if the series converge or diverge. You never have a test to compute the exact value of the series. The exact value of a series, which by definition it's given by limit of its partial sum, n goes to infinity. To be able to compute this, you basically need a way of computing its partial sum. And it's not easy in general to do that. So basically, for all series in this course and with the knowledge of this course, we never ever can compute an infinite series, an exact value of an infinite series. We only use tests to say this is convergent, this is divergent, but never compute the exact value. There are only, except these two cases that I say, there are only two simple series that the exact sum of them can be actually computed in this course. And those are these two cases: geometric series, which have a formula, we have a formula for it, and telescoping series, which is difference of two similar terms with one index different, and then the partial sum, if you write it down, everything cancel in the partial sum except one term from the first term, one term from the last term. Only in these two cases you can compute the exact value of the infinite series. In any other case, if it's not telescoping or geometric, in this course we cannot compute the exact sum of the series. What we can do is to use different tests and different tools that we have to just say this series converge or diverge. That's it, not compute the exact. In this, so that was just basically recap of everything you need to know about series up to test 2. In these two questions, we want to compute these two series, exact value of them. So either they are divergent, or if they converge, finding the exact value of them. So according to what I mentioned, they should be either geometric or telescoping to be able to compute the exact sum. So first, let's do this question. This question, it's very clear that if I consider it like this and then do some operations that I will do later, it should be a sum of two geometric series. Hence, I have a formula for sum of geometric series and I can compute this. That's what should I do for this? So first, as I mentioned, consider it as this plus this. 2n plus 1 over 12n. But a geometric series, I want to write it like this, Rn. So I want the common ratio to the exponent n. This is good to the exponent n, but this is to the exponent 2n plus 1. So let me write it in terms of exponent n. First, extract this extra plus 1. So it's 2 to the exponent 1, which is 2 times that. This is the same as to the exponent 2n plus 1. But this is still not n. It should be n. So to write it in terms of n, I will write it like this. 2 to the exponent 2 to the exponent n, it's 2 to the exponent 2n. Okay, good. For the second term, I have this, I have this, and I have this. Again, I want to have n there, so I will extract one of the frees as the coefficient, and I will write it like this. Now I want, as I mentioned, like this. So a constant, then a common ratio to the exponents n. So I need to have only one term to the exponents n. Here I have multiple terms to the exponents n. So I can consider all of these together as one exponent, as one number to the exponent n. The first one is just 2 squared, which is 4 over 12, the whole thing to the exponent n. Note that I have 4 to the exponent n, 12 to the exponent n. Together is 4 over 12 to the exponent n. In the second term, I have this term to the exponent n, this term, and this term to the exponent n. I combine all of these together. It will be what to the exponent n? It will be minus 1 times 3 over 12, which is minus 3 over 12 to the exponent n. Don't forget that we had this coefficient 3. Write it here. If I simplify this 4 over 12, you get 1 over 3. And simplifying 3 over 12, you get 1 over negative 1 over 4 with this extra negative sign on the back. Now it's exactly looks like geometric series. Good. What was the sum of geometric series? Sigma A Rn. The best way to memorize it, the formula says if it's n from 0 to infinity, it's A over 1 minus R if absolute value R is less than 1, and it's divergent if absolute value R is greater than 1. But this is not the good way to memorize it, because many students, even if this does not start from 0 and start from 1, 2, 3, they use the same coefficient here, which is wrong. The best way to memorize this is that it's the first term of this series over 1 minus common ratio. So when n is 0 and you put 0 in this term, it's AR0, which is A. That's why we had A here. But now you don't, even if you don't start from 0, for example, start from 5. Then your first term is AR5. This should be on top of this fraction. So in the geometric sum of geometric series, you have the first term on top over 1 minus common ratio. So if I apply that for both of these two series, the first term of this series, note that n start from 1. It's when you put 1 in this, you get 2, 1 over 3, 1, or 2, 1 over 3. That's the first term of this series. 1 minus common ratio. Common ratio is 1 over 3. Plus 3 plus first term. First term is 3 negative 1 to the over 4 to the exponent 1. That's the first term because n start from 1. Then 1 minus the common ratio, which is negative 1 over 4. Note that I used these two because I'm in this situation. Here I use the fact that both common ratios, both r's, are less than, absolute value of them is less than 1. Absolute value 1 over 3 is less than 1. Also absolute value negative 1 over 4 is less than 1. Using these two, I can write this sum. Now the rest is just numerical simplification. So I have 2 over 3 over 1 minus 2 over 1 over 3, which is again 2 over 3. This is minus 3 over 4 over 1 minus minus. So 1 plus 1 over 4, which is 5 over 4. No, yeah, good. And then, am I right? So I have negative 1 over 4. Uh, yeah, that's good. Negative 1 over 4. Good. 5 over 4. Then 3 and 2. This 2 over 3 over 2 over 3 cancel each other. You get just 1. This 4 and 4 cancel each other. And you get minus 3 over 5. 1 minus 3 over 5. It's 2 over 5. So that is the exact value of this infinite sum. Okay. Then this is the end of the first question. Now the more interesting question, it's this one. Again, we want to find exact sum. Note that if you this question was not computing the exact sum and you only wanted to see if this converge or diverge, what would the best way to do it was a limit comparison test. I would compare this with only the dominant term. So I would compare this series with sigma 1 over n squared. This would be P series with P equals 2, which converge. Hence, I would conclude that this also converge. So the best way to see if this converge or not, it's limit comparison test. But limit comparison test only give the conclusion to us that this converge. But converge to what number? We don't know. So in this question, we want to compute this infinite series and find the exact infinite sum. So I know that I shouldn't use the tests because otherwise I wouldn't. I would just get diverge converge, not converge to what number. And I know that only in this course, only in two cases or for two series, I can compute the exact infinite sum. One of them is geometric, like this computation that we did in this question. The other one is telescoping series. So this is definitely not geometric. Hence, it should be telescoping series. But it doesn't look like telescoping series in this form. I need to rewrite it in the form that is telescoping. This suggests me that this should be written as difference of two things. But I already know a method to write a rational function as sum of things or difference of things. And that's the method that I know. I can decompose a rational function into sum of smaller fractions. So that suggests me that I should use partial fraction decomposition for this to write it as sum of two things. And hopefully those two things are like telescoping. Let's do that. First, I need to factor the denominator. What is the denominator? It's n minus 2, n minus 1. Now I need to do partial fraction decomposition of this. This is n from 3 to infinity. So I have two linear terms. So contribution of, and multiplicity of both is 1. So I have one contribution for each. And because one lower degree than linear, it's constant, I would have constant sum term. I need to find A and B in this partial fraction decomposition. Okay, let me first combine these two into one fraction. I get n minus 2, n minus 1, a n minus 1 plus b n minus 2. Since this equals this, the denominators are the same, the tops should be the same. So 1 is a n minus 1 plus b n minus 2. Instead of expanding and solving two equations in two unknowns, I would use each linear factor to find one unknown. So at the root of the first linear factor at n equals 2, this equation becomes 1 equals a 2 minus 1 plus 0. So a becomes 1. At n equals 1, which is the root of the other linear factor, I get 1 equals 0 plus b 1 minus 2. Hence, negative b is 1 or b is negative 1. Now, if I write down my partial fraction decomposition, let me call this general term of this series an. Don't write this fraction again and again. Basically, I decomposed an. This is the same as an. My conclusion is that an is sum of these two with a equals 1 and b equals negative 1. Let me put this negative sign between them, and I have this. Oh, that's great. This looks like telescoping because the general term of the series, it's subtraction of two terms, and the index in these two terms, they are differed by 1. So this is telescoping series. And immediately when I recognize it as telescoping, I know that I can compute the infinite sum by using first partial sum. In the partial sum, all terms cancel except one term from the first term, one term from the last term. Let me compute the partial sum. What is the partial sum? By definition, it's sum of a's from the first term. Start is free, not 1 or not 0. It's free. So it's a free, a4 plus up to n, up to an. But to see what are the what terms cancel more clearly, let me also include one term before, which is an minus 1. What is a free? I use, of course, the telescoping version of this series, not of this general term, not the rational function form. A free is this for n equals 3. So it's 1 over 3 minus 2, which is 1, minus 1 over 3 minus 1, which is 2. This is A3. Now A4. It is this for n equals 4. So it's 1 over 4 minus 2 minus 1 over 4 minus 1 plus dot dot dot. Now let me write the last two terms. First, an minus 1. So it's this for capital N minus 1. So what is the first term? This is n minus 1. So n minus 1 minus 2. It's n minus 3. And then this is n minus 1. So n minus 1 minus 1, that's n minus 2. An, it's this for capital N. So 1 over n minus 2 minus 1 over n minus 1. Now let me cancel them. Let me use another color to cancel. Negative 1 over 2, 1 over 2. Negative 1 over 3 cancel something here that I haven't written. This cancel this cancel something here that I haven't written. Basically, only this term and this term survive. As I mentioned, always for telescoping series, if the the index difference between these two, it's 1. in the partial sum, you get one term from the first term, one term from the last term. Everything else cancel. Basically, we can say it's the term in the first term. You should keep the one with lower index one, not the two one, and the term in the term with in the last term out of the two term, you need to keep the larger index term. Okay, we computed Sn, so the conclusion is that Sn is this, which is 1, minus this. This is an explicit computation of the partial sum. Now, by definition, an infinite series or an infinite sum is the limit of its partial sum. But its partial sum is this. So I need to take the limit of this thing as n goes to infinity. As n goes to infinity or becomes larger and larger, this approach to 0, 1 over n minus 1, it's 1 over infinity, which is approaching to 0. So you get 1 minus 0, which is 1. That is the final answer for this question. So basically, this infinite sum, infinite series, it converges to exactly to the number 1. Again, the only cases that you can compute a series and converge to which number exactly, it's only telescoping case and geometric case. In all other series, in all other examples in this course, we won't compute the series. We use many tests that we have to only conclude if the series converge or diverge. Not compute if converge computing converge to what number. Okay, that's everything that I wanted to do. I hope that this was helpful. And again, let me emphasize that I haven't covered everything. For example, I haven't covered sequences. I haven't covered improper integral. So make sure that you review everything that is missing in this review questions. Thank you.